Okay, welcome back. So we're moving on to section 17.3, which I don't actually have a super good version of in my ODEs book, so we're going to stick with this book for this section. And it's moving on to kind of the more general interpretation of inner products and norms, mostly as they apply to function spaces now instead of just vector spaces. Now, understandably, all function spaces are vector spaces, but I think you've all gotten very used to thinking about inner products just as dot products on finite dimensional vector spaces, and in particular like R3 or something like that. And so today, what we want to think about is that inner products can be defined much more generally than just the dot product we're used to. Okay, so from now on, I want us to stop assuming that an inner product will take the form of a dot product. It's this hard thing we have to do where we kind of pretend like we forget what used to be true, and now take what I'm going to define following as like the actual definition, and we'll just see that the dot product is like an extreme subset of this definition. It's something that we can think is sitting there, you know, kind of at the edge of our mind, but we really want to start thinking about the inner product as what I'm going to define now. It's not necessarily a dot product. You can think about it slightly like a dot product, but I would actually rather you think about it strictly as what I'm going to define. Okay, so the inner product, we're going to start with the definition right here. An inner product on a vector space, and they're using just a field F here. Think about this as C, the complex numbers. Okay, so inner product over is vector space over the complex numbers is, and get rid of bilinear here too. So sesquilinear, which I know is a weird word, but let's just think about it as a function of two inputs. There's my two inputs. I'm taking two elements from the vector space, and I'm going to gain a complex number out of those two elements. So let's just jump back really quick to the dot product, and I know I was trying to tell you that we shouldn't think about this like the dot product. But let's take two complex valued vectors, take their dot product. What do we get out of these? Well, the dot product says I multiply across, and then I add those multiplications. So this is 2i minus 2 plus 2i. And so what we get out of that is negative 2, which is an element of the complex numbers. So what's happened here is you take two vectors. The dot product was saying, if we jump back to the dot product says I am able to intake two vectors and I'm able to output a complex number. We're going to do this in general now. I'm able to intake two vectors and I'm going to output a complex number. That's what we want to think about the inner product. And yet the two vectors that it intakes have to be, the way that the inner product works over those vectors has to be relatively well defined. It has to, this sesquilinear means it's like the dot product, which itself was like multiplication. Okay, so we want to think about it, hey, this is kind of behaving like I'm multiplying the two vectors in some abstract manner. Okay, it has to satisfy the following conditions, and I know this is a lot for you to take in. There's a whole lot of words, a whole lot of math sitting around here. Think about it right here. If I think about taking the inner product of two vectors, conceptually, if I take the dot product of two vectors, the only way the dot product of a vector with itself, right? So the only way a dot product of a vector with itself is going to give me 0 is if that vector was already 0. I can definitely take the dot product of two different vectors and get 0. That's what orthogonality is. But if I'm taking a dot product with itself, if I multiply a vector by itself, there's no way that that's going to send me to 0 unless I started with a 0. But this should be true of kind of this more abstract object that we're working with. Positive definite means that similarly, if I take it with itself, I'm asking how parallel is a vector with itself? What is the degree of parallelness? Well, that should be a positive number, right? The degree of parallelness should be a positive number of a vector with itself. It should never be able to be orthogonal or anti-orthogonal. A vector never points in an opposite direction to itself, and so we need this idea of positive definiteness, which just says that if I take the inner product with myself, I get a positive number out of it. So symmetry is only true in the real setting. In the complex setting, it's called sometimes conjugate symmetric. where actually if I swap the order of B and A, then I actually have a little complex conjugate of the solution. So let's just keep that in mind, that symmetry is a little bit iffy on these. If it's real valued, sure, symmetric is true, but otherwise it's conjugate symmetric. And then finally we have this property. This is really the bilinear property or sesquilinear property, because if I put a linear combination into one part of the inner product, then what happens is alpha A plus B comma C. What happens is we're allowed to split. You're allowed to split over addition. So splitting over addition would give me alpha A comma C plus B comma C. And you're also able to pull scalars out front. So I can pull alpha out front, and that gives me alpha A comma C plus B comma C. So these are the properties that an inner product needs to satisfy. One could verify that, in fact, the dot product does satisfy these. But there are a lot of other definitions. We can define all sorts of other maps or really quantities on functions or other vector spaces that don't necessarily look like a dot product. So yeah, the dot product satisfies these, but there's all sorts of other things which still satisfy these, and these are really the inner products. The dot product is just the special case of these. And if we had a term in the second case and we wanted to pull it out front, we would pull it out front as a conjugate because of that conjugateness in the second entry. So let's do this exercise really quick. So it says verify that the dot product for Rn and Hermitian inner product for C are indeed inner products. So let's jump to the whiteboard and let's verify this. So verify if I can spell, dot product is inner product. So the way that these verify ideas work is that we just have to show that the properties are satisfied. Show properties I, double I, triple I, and linearity are satisfied. And to do that, we're just gonna start with the dot product in Rn and recall the definition of the dot product on Rn is that the vector A dot the vector B is defined by the sum of the entries of A against the entries of B. And maybe I'll use a J so we don't get confused with like the imaginary number I. J from 1, J from 1 to n. That's the definition of the dot product. In a slightly more abstract sense, using my summation notation, that's the definition of the dot product in Rn. And let's just see that number 1 is true, which was that if I take A and I get 0, then A equals 0. We want to make sure we have our ordering correct. We don't get to start with A equals 0 and show that it's 0. We have to start with the inner product being 0 and then claiming that A is 0. But it's not too hard because if I compute the inner product of A and A, which is the dot product in this sense, if I use my definition, right, my definition is right here. If I use this, then what I recover is the sum from J going from 1 to n of AJ times itself. Any number times itself is squared, and suppose that this is equal to 0. So we suppose it's equal to 0. That's me supposing that. If that, then the other one. Can I claim that my vector was 0 in the first case? The answer is yes, because every square number is positive, or it's non-negative. So each of these are non-negative, and if I add n non-negative numbers and get 0 out of it, if I add 1, 4, 11, and 26, that's a positive number. So the only way to gain 0 out of the sum of non-negative numbers is if in the first case all AJs are 0, right? The only way that could possibly be 0 is if all of the AJs are 0, and so the original vector was equal to 0, which is what I wanted to be true. So let's see number 2, which said that if I take A with itself, I get a non-negative number, or rather that it's strictly positive when A is not 0. Same thing. And we're going to get the same thing here, right? Because an inner product of A with itself, when that happens to be the dot product, is exactly what we had written before, j equals 1 to n, aj squared. And since all of these are non-negative, because they're square numbers, then in reality, that has to be non-negative. And by 1, which we already showed, is only 0 when a is 0. And so that's me showing that 2 is true. Finally, when it comes to 3, this is symmetry. I want to show that A inner product B is B inner product A conjugate, right? Except we're dealing with real numbers here. When it's real numbers, I don't need a conjugate. And this is easy enough to prove because by the definition of the dot product, if I'm using the dot product here, j equals 1 to infinity. J equals 1 to n. aj bj happens to be, thanks to multiplication working the way it is, bj aj, not infinity, which happens to be the inner product of b and a. So there's verified 1 through 3. Let's just verify linearity of dot product. Linearity is not too bad. If I take alpha a plus b comma c, when it's the dot product, this is alpha a plus b dot product c, which is defined by alpha aj plus bj cj, it's the sum of j from 1 to n. And thanks to the definition of sums, right, the way that sums and multiplication behave, that sum has to be the sum, or alpha times the sum, j equals 1 to n. I'm distributing aj cj plus the sum, j equals 1 to n, bj cj, and this happens to be equal to alpha a dot c plus b dot c, which is what I wanted, alpha inner product a and c plus inner product b and c. And so that's linearity for you. I'm not going to do the Hermitian one. I'm actually going to assign that for your homework. This one right here, that the Hermitian inner product is also technically an inner product. So that's the definition on the complex numbers. So I'll sign that for the homework, but you can go back to this part in the video and rewatch it and basically try to repeat everything that I just did with now the Hermitian inner product instead of the traditional dot product. But that's how one would go about showing that something actually satisfies everything in this definition. And then we're going to move on to this notion with the Schrodinger equation. So this is, given the Schrodinger equation here, we have the solution in a box, right? So given the specific boundary conditions, we can actually construct the one-dimensional solution for the particle in a box, and we happen to have that our solutions were indexed by this lowercase n. And this was true for any n in the integers, n in z. And because of that, we can think about these, we can form a vector space out of these as a basis. And forming a vector space out of those as a basis gives us the following, gives us this, that actually any solution, since each one individually was a solution and the differential equation is linear, then after combining all of them into a vector space, which is what's given right there, after combining all of them into a vector space, we actually recover another solution, which is this solution right here. And so this in many ways is the general solution. And you'll recall that the previous video I was describing how the general solution to linear ODEs forms a vector space. So this is the vector space of general solutions to the vector space of, I guess it's the single general solution. The general solution is the vector space as a whole. Vector space of general solution to particle in a box. Schrodinger equation. Schrodinger equation. So there's your general solution, and it is the vector space. You can see these a sub n's really are the coefficients or the entries to the vector, and then the psi sub n's, which are these, are the basis elements of that vector space. So So yeah, we can form a vector space given all of our individual solutions. We can just add them together under some infinite linear combination, and that forms the vector space of general solutions. Now the question becomes, we're in the inner product section, right? Next exercise shows it's a vector space. We're in the inner product section. The real question becomes, can I form an inner product on some sort of vector space which has infinitely many elements, right? So I have an infinity of elements here, or basis elements. Can I form an inner product? And the answer is yes. So here's how we're going to propose proposed inner product. On the vector space of solutions to Schrodinger. And if we ended up going through the work, we have to show that this actually satisfies all of the properties of the inner product that I described above. But what is it saying first? Before I show that, what is it saying first? It's saying I multiply, so both of these are solutions. So both are solutions. What I'm going to do is I'm going to multiply them. I'm going to take a conjugate on the second one, which is common for complex valued vectors, right? And then rather than, this is very similar. Think about this as the sum over j being going from 1 to n. Think about that as a sub j, and think about this as the conjugate of b sub j, right? So this is, in some ways, this is like the continuous analog. I think when we think about Riemann sums are the continuous analog of series, right? This is a Riemann sum that produces an integral. So it's the continuous analog of the series. The continuous analog of a finite vector is a function, because an infinite vector is a function and interpreted in the right way. And then similarly over here, the conjugate of the elements of the function, or of the elements of the vector, are just this function. So this really does take on the same structure that our dot product took on, but it just looks a little bit different, right? We have an integral, we have multiplication of functions, and we still have the conjugate sitting around there. So that's how we're going to define the inner product on this function space. And let's just verify that this is an inner product really quick. So what we have here is, let's verify sesquilinearity. This is that weird word where if I'm putting, I should be linear in this term, so I should be able to split the inner product here at the plus sign, and then the alpha should be able to pull out, but it should be conjugate. That's the sesquilinear part or idea here. But let's just verify. So let's write this out by its definition. So its definition just says I'm going to multiply that and this, and there it is. So I multiply the two of them, but I take a conjugate on the second, and then I integrate against the whole thing. So I'm going to describe it as a massive integral. And then because of my properties of conjugation, complex conjugation is able to distribute all the way down to all of these. And when that happens, the conjugates come down. I have too many terms there. When that happens, the conjugates come down, and I end up with phi conjugate, I end up with alpha conjugate, and I end up with theta conjugate. And then because of the properties of integration, I'm also able to distribute integrals over plus signs. So I push the integral to both sides of the plus sign there, and so I pick up two integrals on each piece. And because of that, that's what gives me sesquilinearity. Once I get rid of that extra term there, that's what gives me sesquilinearity, because if I look at each of these pieces individually, those are individually the two inner products that I wanted to start with. So this inner product does have that nice property of, like, I'm able to split it over plus signs. And then I definitely get 0 if I plug both, if I test 0 with itself. I get a non-negative number here. Let's jump down a little bit farther. I get a non-negative number if I take the inner product of psi with itself, and that's just because psi on x and psi on x conjugate dx, when I take a complex number and multiply it by its conjugate, I recover the complex magnitude of that function. And because the complex magnitude of something is always positive, I recover that the inner product of phi with itself is always positive. So that's where I gain my positivity, and we can check symmetry, or rather conjugate symmetry, directly by computing both of them, both directions, and we would find out that yes, in fact, the results are the same up to conjugation. Okay, so that's inner products in a nutshell. And a lot of times, so if we're taking inner products of functions, I want you to emphasize this. This is basically the only way you're going to take an inner product of functions. And then the equivalent formulation, inner product of vectors, always looks like this, right? The one that we were looking at earlier, j equals 1 to n. So functions, vectors, This is A vector, inner product B vector. And you can see the similarity between the two of them. You think about the Riemann sum converging to the integral is the way I like to think about it. So maybe freeze frame it right here, just so you can say, hey, that's the inner product of functions, that's the inner product of vectors, and basically for the rest of the semester, you'll just want to keep these two ideas in mind for inner products depending on the spaces we're working with. Let's move on to norms. It shouldn't be too much of a stretch to believe that you can always recover norms. In the complex case, we recovered a norm by taking a square root of a complex number by its conjugate, and it's not a stretch that you can define a norm on any inner product space just by computing the square root of an inner product with itself, right? And this would agree even in finite dimensions, where we would recover the Euclidean metric or the Euclidean distance from zero. This is how we were considering norms of vectors, and we can do the same thing with functions. So all I have to do is, so to compute, let's test this really quick, compute the norm of psi as a function. I'm going to take the square root of psi as a function with itself, which you'll recall the definition of the inner product of psi with itself was the integral 0 to L psi x squared. Maybe I should get rid of an x here so it doesn't look like I'm computing it on a specific point x. I'm really just computing the norm of that function. Here, this is the complex magnitude of psi. And then I'm integrating that, and then I'm taking a square root. So that's how we would compute norms of functions. So every inner product is going to give me a norm just based off of that idea. And really, we can still think of norms as the distance from zero in some sort of an abstract setting. Anyway, that's all I have for you today. Thanks for sticking with me. I'll see you in class.